Hey everyone. All right. Make sure I'm not doing a bandwidth and a functors, eh? Ah, secret background work. Shh. Don't look at those. That should be. Where am I? Zoom. Right. Yeah. So we're not doing anafunctors. We're doing regular functors. Okay. So last time we ended up with a definition of category, and I suggested you might wish to go away and look up some examples. This is what I want. All right, so I'm going to give you a bunch that are relevant for the course. So I mentioned set, the category of sets, RMod, the category of R modules, and linear functions. So I generally, so categories generally named for their objects. All right. So the type of maps are usually implicit and sort of by common convention. There are some standard things, like R modules. Well, the R linear maps are sort of the obvious maps, so we use those. So let's just quickly note down some other categories. So the category ring of rings, so that's the objects, the morphisms, ring homomorphisms, the category of directed graphs. So objects are directed graphs. Morphisms are maps of these. Cochain complexes. So let's just call this CPLX. Maps of these. So in all of these examples, you can check that composition is associative if you have identity maps. Here's one which we haven't really seen, but it'll kind of be floating around in the background. I might call Z graded. I want to move that. That's too close. All right. Hurry up. So what do we call this? GR RMod. So the objects are Z graded. I'll tell you what these are in a moment. R modules. and morphisms between them, right? So you've got to think, what is a Z-graded R module? It's an R module of the form, let's say, I call it M bullet, which is a countable direct sum of R modules. So if we have any collection of R modules, then we just take their big direct sum, so any collection, any countable collection, and we take their direct sum and we say that's a new R module, but we remember the fact that it's this specific direct sum. Peter, no. I'm just thinking of it as an arbitrary ring, as we have been. Graded rings are something which we may come across later. Okay, so what's a map of graded R module, Z-graded R modules? Well, it's a collection. Well, it's a map of modules which is equal to the direct sum of maps between the different m's and the different n's. Like so. So one way you can think of it is actually just a countable collection of maps. We can throw it all into a map between these single modules. So another way of thinking about it is maybe f from m dot to n dot, such that it maps the nth graded piece into the nth graded piece. So we've seen an example of this before. I'm just going to slide slightly over here. We defined the two cohomology modules of a directed graph, and we define H bullet, say with R coefficients, to be H0 direct sum H1 direct sum. So we don't have to have infinitely many things here, and in practice for negative integers these modules will be trivial. And so for any finite number of modules you can take their direct sum and think of them as Z-graded, where outside the sort of finite range where they're interesting is just 0, because the direct sum, the 0 module, does nothing. Okay, so here's another example, which is a little sort of, if you like, toy example. So we can actually just write down an algebraic structure which is like finitely many objects, finitely many arrows, and check that it satisfies the category axioms, and it's a category. So here's, I haven't got a name for this one. I think I called it something in the assignment. And I need identity maps everywhere. Right, so this has got two objects. And it has 4 morphisms. The identity morphisms of the 2 objects and 2 other ones, which I'm calling sort of partial 0 and partial 1. Partial 0 dot gives you 1. Partial 1 of dot gives you 0. So that's, I mean, that's the whole package. Right, so the objects are precisely these two little finite sets. I don't think so, Space Kitter. Usually bool denotes the category of Boolean algebras. There's some various types of morphisms, but if you're thinking about bool as in like truth values, like true and false, usually that has only a single map from one object to the other object. So that's another example. Let me just write that down. Here's an example. I have two objects called 0 and 1. No, not do 0, I'll do t and f. F and t for that matter. I have identity of f. I have identity of t. And this other map, which I'm not going to give a name to. And so the composition, I haven't defined what composition is in either of these two examples, but the only non-trivial compositions are with identity morphisms, and they're determined by the axioms of a category to do nothing. So we don't need to specify any non-trivial compositions here. If, for instance, this one pointed in the other direction, this partial 1 pointed in the other direction, we'd have to say what the composition of partial 0 followed by partial 1, or partial 1 followed by partial 0, and that would have to be a map, right? So that would have to be a morphism in the category. And if what I've got here was my only options, the composites would have to be the morphisms that are there. But we're doing this one instead. Okay, so last one I'm going to drop, name drop, is something about spaces. Let's say call it top. So the objects are topological spaces and continuous maps, continuous functions. I use the word maps a lot. And I might just put a little disclaimer here. I might say this is some topological spaces, because we might be interested in putting restrictions on what sort of topological spaces we have to capture what we are hoping that topological spaces are going to model. And for some people might be interested in like topological manifolds, and that's actually quite a bit smaller here. But it's the sort of thing where you say I've got all arbitrary topological spaces, they're quite horrible, and I'm interested in certain behavior, and so I might put some extra axioms on them. All right. Any questions? Drop an object in the chat. H-top, yeah. We'll get to that, Chris. Drop your favorite collection of things in the chat, and we can see if it's a category. I mean, it probably is. Some things are a bit tricky. The interval object schemes. Yeah, so you can pull out your own experience of maths here and think, what objects do I know about? Varieties, yep. Yeah, so one quote which I particularly like, which is one of the early workers in category theory, is that category theory makes that which is trivial trivially trivial. Like, it sort of encodes things in such a way that, well, it just kind of follows from abstract properties, and then you can sort of strip away that stuff and then say, what's the actual specific things in this subject where I have to not just do formal category theory, you know, like a little piece of analysis or some hardcore algebra or something, but you've used the category theory to set up a formalism where you remove all the bits that should be trivial. Regular expressions, Jim Taylor. Some kind of syntactic thing. That's a bit tricky. I mean, don't really know how, if regular expressions would be the morphisms or the objects. Yeah, there are some really interesting computer sciencey type examples, like lambda calculus and so on. Although apparently not Haskell. Haskell is the things in Haskell, a programming language, work like they are objects of a category, but apparently they're not. And there's some technical reasons which I don't understand. All right. But we are interested in the interplay. Let's see, scroll down a little bit. Well, ultimately, we want to go from spaces, number up to complexes, and then from complexes to graded modules. Possibly via something combinatorial, which we're going to Tyson, the category of categories. It's not bad. I don't know what you mean, what is it like? But it's one I have worked with. All right, so yes, so I'm just okay. Space Kitcher has enlightened us why Hask, the category of Haskell types, is not really a category. Interesting. Yeah, but Tyson gave me the chance for a perfect segue. Objects of the category of categories, say the category of small categories. What are the morphisms between categories? And this is really what we want. Well, it's halfway to the motivation for categories in the first place. So here's definition. Functor is a map of categories. Make my C's a little bit curlier. Right, so what is a functor? It goes from C to D. So the data consists of a mapping from the objects of C to the objects of D, which we're going to call F. And we're going to overload notation here a bit. We'll be applying F to objects, but also to morphisms. And I was writing little a's and b's and so on for objects yesterday, but I'm going to switch to x and y because they're the other end of the alphabet to C and D. So I don't want to get things confused. For all objects, x, y, C, so it takes a morphism in C from x to y, and returns a morphism in D from f of x to f of y. With some axioms, I want f of the identity to be an identity. And then here's the most important property. This is the Functoriality Property. I want f of x to f of y can be so I can apply my functor to a pair of morphisms and get these two gizmos and then compose, or I could compose first and then apply f. So that's my data on the top. That's my conditions down below. This is all f in C x, y. And G, a morphism in C from y to z. Maybe I should even I can rewrite it on a different line like this. I could write it like this, or so it should look like a homomorphism in some sense. But it's a homomorphism that's applying itself to morphisms of things. Okay. So there we go. So this condition in this second box is called functoriality. And this is really the power of functors comes from. So one corollary of this is that if I have something that's an isomorphism in a category, like it's an isomorphism of directed graphs, and I apply a functor, for instance, as we'll see, that's a bad example. If let's just say I have something, a functor that takes a topological thing and gives me an algebraic thing, which is kind of the point of algebraic topology, then if the topological things are isomorphic, the algebraic things will be isomorphic. So if I have an isomorphism, the functor sends it to an isomorphism. Whereas if I have something, an arbitrary map, and I wonder, is it an isomorphism? But I can't tell from its description, I apply the functor, and if it's not an isomorphism now, then it couldn't have been a functor and it couldn't have been an isomorphism to start with. The sort of converse behavior is more subtle, but it's a way of checking if things are could be the same or not. All right, so what are some examples of functors? I mean, there are some less complicated ones. So for instance, there's the inclusion functor of set into directed graphs. So it takes a set and returns the graph where gamma naught is that set and gamma 1 is empty. So it returns the graph with a specified set of vertices and no arrows, no edges. So we could say set is a subcategory here, but it's not essential. Here's another one. It's similar. I could take R mod. It's a functor. Sends to graded R mod. Takes M and sends it to sort of what do I want to call this? Maybe something like M0. So this is a graded thing. It's M in degree 0. So if you like, wrong way around. It should be n equals 0. So we've taken some information, some object, like first one's a set, second one's a module, and we've placed it in a richer context. So we haven't said what this does to morphisms. But if I have a function between sets, then it will give a map between the corresponding corrected graphs that we've constructed in this way. And if I have a R linear map of R modules, it'll give a graded map of graded R modules. Because it's just mapping things in degree 0 to things in degree 0. And everywhere else is trivial. And there's another thing you can do, like this isn't the only one, but also I could do this. I could send M to M constant in degree n. Let's call it K. So now if I want to think of this as M K, so in degree n, it's M if n equals K and 0 otherwise. So a graded R module, it's a little bit similar to a cochain complex in the fact that you've got a sequence of modules. But in a cochain complex, you've got the data of the differentials and the property that two of them, any two adjacent ones, compose to 0. Here we just have a bunch of modules, and we can just sort of smash them all together, take the big direct sum, and we have a single module, but we've remembered that it's actually built out of this sequence of modules. So these things are related, but they contain different information. Typically the graded things are smaller. Just one moment. Sounds like someone's having fun in the other room. Okay. All right, but as a counterexample, okay, just seeing where I'm at. Okay, that's set going to R mod, right? What are other constructions we've looked at that take objects of one sort and give us objects of another sort and do something nice on maps? There's not a functor that does this. invite people to think about why that might be so. And I'm just going to think about that while I just quickly grab a drink of water. I say think about it and refrain from writing your answers, and when I get back I'll ask. All right. So Chris, it's a good first point. Fails to be functorial. So Space Kitter, I'm not quite sure, but I think I know what you mean by cofunctor. And Tyson has said contravariant. So what does it mean to be a functor, right? Sure, I'm writing color. S maps to T does not give us a function from S to T, does not give us a linear map that way. So what it does is it goes the opposite way, right? The map goes from RT to RS. So to handle this behavior, we need to quickly look at, say, what an opposite category is. So it's safe to assume that opposite categories are just a technical trick to take care of this behavior. How there are functors, well, things that you would want to be functors, but they do not quite the right thing to arrows. See, it's denoted C op. It's the same objects as C, but we just define formally that the morphisms in C op from X to Y are precisely the morphisms in C from Y to X, which seems like a bizarre thing to do, but it really comes into its own when you see what happens if you have a functor from C op to something else. Yeah, and so you might think, what is composition? Composition, I need Y, Z, but what is this? This is the same thing as, and I'm just going to swap the order of the Cartesian product, is C from Y to X Z to Y. Now we can do composition in C, because I've got something from Z to Y and something from Y to X. C Z X. This is the same thing as C op X to Z. So that gives us a functor. That gives us a composition map. So why do we care about this? It's because a functor from set op to R mod is what we are looking for above. So the objects are sets and a morphism from S to T is a function T to S. So then a functor, well, this specific functor the construction, a set mapping to the functions to R is a functor set op to R mod. How do we see this? All right, we have to say what it does on objects. We know that bit already. And morphisms. Right, so it sends something in set op from S to T to something in R mod from, and now we have to swap things. Comes RT RS. And this is this behavior we saw already. To RT precompose with F. Yeah, so this, a functor from an opposite category like this is sometimes called a contravariant functor. Maybe sometimes a cofunctor, but contravariant is usually the adjective that people use. And so, given that we have set op to R mod, remember we use this construction to build the cochain complex of a directed graph. Which takes directed graph it gives me a complex of R modules. I probably should have said CPLX sub R. So cochain complexes of R modules. And what it does, it's C bullet blank dash R. So it takes a graph and sends it to the cochain complex of R modules. And as we saw, when we have a map of directed graphs, we get an induced map of chain complexes in the other direction. Objects like that. And there's a further functor takes a directed graph and gives me a graded R module. Takes gamma and returns back the sum of the two cohomology modules. Right, so these are the kind of little hands-on constructions we've done, you know, like literally with matrices and so on. But we can encode them all in these sort of abstract ways, so that when we can no longer use like by hand methods like matrices, we can start to rely on these abstract machineries to take care of all the formalism. Any questions? I should say what functoriality means for these sort of contravariant functors. So if I have, let me write down the generic case. F is a functor from C op to D. Then what is it? There's an assignment on objects. And then there's an assignment on arrows. Let me write this the other way around. But C op from Y to X, morphisms in Y op from Y to X are the same thing as morphisms in C from X to Y. So it's an assignment at the level of morphisms. It takes something going from X to Y, maps it all the way over to F of Y going to F of X. And then functoriality, what does that do? That says that F of X, go the other way. The composite in this order is equal to F of, let's call this H, F of G All right. Okay, so that's literally just a whole whack of abstract category theoretic nonsense. But the important thing is to go back to the examples that we've been working with so far and see how you can recognize what we've been doing is encoded by this information. Now this is just garden variety abstract nonsense. Space Kidder. Generalized abstract nonsense is even more fun. Alright, so I want to make a quick definition. So let's go back to our sort of subject matter. Alright, so we had, alright, what do you think about directed graphs? They have Euler characteristics, which just gives you a number. And it's quite a it's an invariant of a graph that's not especially rich. Right? It's a single number. Sometimes it can tell apart things, but often it can't tell things apart. But what we're interested in is when is it that two graphs have the same cohomology, and not just to have the same cohomology, but when is a map between the graphs given isomorphism on cohomology? Because it's not just about two graphs floating around and it just so happens that, well, maybe the cohomology modules are isomorphic. What we want is an actual map of graphs which somehow reflects the fact that they're the same shape, or have got the same topology, and we can see that algebraically. Okay, so here's a definition. We have a map of directed graphs. So H, call it isomorphism. If an isomorphism of graded modules. So by saying graded R modules, it's really just saying it's isomorphic at the level of H0. Sorry, there's an isomorphism at the level of H0 and an isomorphism at the level of H1. Induced by the map of graphs F. So sometimes the cohomology modules may be isomorphic, but a given map of graphs doesn't induce an isomorphism. Okay, so what is this? So let's take it matters which map you pick between the graphs. So let's take this pair of graphs. We saw something similar earlier. This is P. Right, and it takes the two vertices to the single vertex and the two edges to the single edge. And you can check this is a map of directed graphs. Then you can do a direct calculation. That's not it. I mean, and this is cohomology with implicit integer written in there too, but just for space I won't. So for instance, this is G, so the cochain complex associated to G is a pair of copies of the integers, because there's one vertex. Yeah, there's one vertex, so we get a copy of Z here. There's one edge, so there's a copy of Z here. But the map is the zero map. So its kernel is its kernel is Z and its co-kernel is Z. And a similar thing, not a terrible calculation for gamma, it's Z2 mapping to Z2. Kernel is Z, the co-kernel is again Z. But the actual induced map, P star here, this is an isomorphism. H1 of G to H1 of gamma. Does anyone want to hazard a guess what this might be? Just random uninformed guesses, I don't mind. So I'm claiming it's not an isomorphism. What's they say? Wrong answers only. Any advance on 2? Just divide by 2. So Razor Friendly has indeed hit the nail on the head, or as someone I once knew said, hits the head on the nail. This is a multiply by 2 map. So you think of P as something like, I'm taking the unit circle in the complex plane. It's things of the form e to the I theta, and then I square that complex number. It gives me a map to the unit circle in the complex plane, but it's like the boundary of the Mobius strip. It's a non-trivial map. It winds around twice. So essentially, let's just say this is what's going on here, except it's a purely combinatorial result. Right? It's nothing to do with continuity or anything. It's just, this is a 2-to-1 map at the level of vertices and edges, and it sort of wraps the right way. Okay, so I'm going to end with a proposition that we're going to explore in the tutorial this week. So it'll be like group work. Let's see how we can figure out how to prove this thing. So proposition sort of fulfills a promise that I something that I hinted at earlier. So let's let gamma be I'm going to say directed polygon. All right, so what is that? It's a finite directed graph. One big cycle in the undirected sense. And I can order the direct the edges however I like. Right, so that's my assumption. Then, indeed, it's cohomology. I should probably throw some z's in here. Well, okay, without anything, it's a z. Okay, too excited. Stop going too fast. All right. And as a corollary, so we have a finite disjoint union of polygons we get that these are of n polygons, then this is the direct sum of that many copies of z, which is just z to the n. All right. Maybe one more. No, we'll jump on that next time. Okay. We can chat some more over on Discord. I'll get this video up on YouTube. Yeah, so we can prove this with the technology. Tommy, yes? Sure thing. To ask away. So we can prove this with the technology we've got right now. Okay, Tommy, we can have a chat about that offline. Yeah, we'll have a chat, and it'd be easier that way. Cool. So with that, keep safe. Hope people who got together at UTS today had a good time actually seeing people. All right, well, let's head on over Discord and we can have a bit of a chinwag, and I'll sign off.